What is frequency response in electrical engineering transfer functions? Have you ever wondered how electrical systems react to different frequencies? Understanding frequency response is key to grasping how transfer functions work in electrical engineering. Let's break it down. Frequency response refers to how a system or circuit reacts to various frequencies of an input signal. It focuses on two main aspects: amplitude, which is how much the output signal's strength changes, and phase shift, which indicates how the timing of the output signal compares to the input signal. Transfer functions are mathematical representations that describe the relationship between input and output in linear time-invariant systems. They are usually represented as Hs, where S is a complex frequency variable. To find the frequency response, we substitute S with j omega, where j is the imaginary unit and omega is the angular frequency. This gives us a complex function that shows how the system amplifies or reduces signals at different frequencies and how it shifts their phase. Frequency response consists of two parts. The first is the magnitude response, which tells us how much the output signal's amplitude is scaled compared to the input. For example, if the magnitude is 1, the output matches the input amplitude at that frequency. If it is less than 1, the output is attenuated. The second part is the phase response. This shows the angle or phase shift of the transfer function at each frequency. It reveals how much the output signal is delayed or advanced in time relative to the input signal. In practical applications, frequency response helps engineers analyze how circuits like filters, amplifiers, and control systems behave with sinusoidal inputs of varying frequencies. For instance, a low-pass filter allows low frequencies to pass with little change, while it reduces higher frequencies. To calculate frequency response, we evaluate the transfer function by substituting S with j omega. Engineers often visualize this data using Bode plots, which display magnitude in decibels and phase against frequency on logarithmic scales. Consider a simple resistor-capacitor circuit. Its transfer function changes with frequency. At low frequencies, the capacitor acts like an open circuit, resulting in specific output values. As frequency increases, the capacitor's reactance decreases, altering the output's magnitude and phase. At the cutoff frequency, the output magnitude drops to about 0.707 of the maximum, which is also known as the -3 decibel point, and the phase shift is -45 degrees. At very high frequencies, the output magnitude approaches 0, and the phase shift nears -90 degrees. In control systems, frequency response analysis is vital for assessing stability and performance. Engineers examine how systems respond to sinusoidal inputs at different frequencies, often using tools like Nyquist or Bode plots derived from transfer functions. Frequency response in electrical engineering transfer functions is essential for understanding how output amplitude and phase vary with input signal frequency. This knowledge is crucial for designing, analyzing, and controlling electrical systems effectively.